Thank you. I appreciate that. Good day to everyone, and thank you for taking time to join our webinar today. My name is Caroline Brown, and I'm the Channel Account Manager with Fluke Networks supporting ADI. For those on the call today that are not familiar with Fluke Networks, we specialize in providing copper and fiber test solutions for verification, qualification, and certification of structured wiring solutions. My colleague, Jim Davis, who is our regional marketing engineer and has over 25 years of experience in the industry, including working on international cabling standards committees, will lead you through the concepts of test parameters for twisted pair cabling and principles of testing, troubleshooting techniques. So Jim, I'll hand it off to you and take us on our journey.
All right, super. Thank you, Caroline. Good morning, everyone. My name is Jim Davis. I'm a regional marketing engineer with Fluke Networks. Today, we're going to go through really one of my favorite presentations, and we're going to take a look at what is it that we're looking at in the cabling, the copper and fiber that allows us to support very high-speed communications. Again, this presentation is for you. I appreciate your coming out. Please feel free to send in some questions. We'll see if we can't get to those. Real quickly, I work for Fluke Networks. We make test equipment. We don't install cable, we don't make connectors. We make the tools that the people who install those cabling connectors use to make sure they're properly installed. And then in the day-to-day maintenance, the question often comes up, is this device on the end of the cable, is this wireless access point, is the security camera, is it broken? Or is the cable broken, or is the device at the head end? And we always want it to be the cable because cable breaks, people step on it, cars drive over it. And that's pretty easy to fix if we know it's the cable. Our tools will help you to determine if there's an issue with the cable, where the issue is with the cable, and also if there's not an issue with the cable. We can say that. They don't really want to go and reboot the server if that's not the problem. All right, get up on my soapbox here for a minute. Why is it that we certify, why is it that we test structured cabling? I may be buying perfectly good jacks, perfectly good cabling, and I might have an installer who has a piece of paper who says that he went to one of my presentations. That doesn't mean that the installed cabling is going to be as good as the components. We want to make sure that it was properly installed. This is also a way that people get paid for the job. Before I make that last payment, I'd like to see the certification to know that the cabling is in good shape. If I wait until I plug in the active equipment and it doesn't work, sometimes it can be a challenge to get that cabling contractor to come back. Experience shows us that certified networks run faster and support future applications better. There are going to be fewer physical layer errors in the transmission. And that cabling is, boy, as much as there's a cost of the cable and the connectors, installing the cabling is expensive. It's going to be there a long time. I often get the question, which component should I use? Which brand, which model is better? And then my boss comes in and says, but here's your budget. And so I don't want to spend all my budget on getting gold-plated solutions, gold-plated products, if that's not what I need. So you can consider less expensive components, but the certification will make sure that that's a low-cost Category 5E cable and not an expensive Category 3 cable. And I always throw this out. Be careful of those people who offer to save you on the installation by not certifying. This cable is so good, you don't have to test it. If that cabling was so good, wouldn't you want to test it to show me how good it is? Let me get off my soapbox here. All right, so why is it that we want to follow the standards when we're doing our installation? The standards have been developed over many years to help out with interoperability. I may buy cable from one connector, I may buy cable from one manufacturer and connectors from another manufacturer, or I may buy one camera and I may replace it with a better camera that has more features, that has better software, but I want it to plug into the same outlet. I don't want it to need a proprietary solution. And then I want to think about the future as well. So the standards that we're going to talk about in North America, most often we come across the TIA 568 standard. Internationally, there's the ISO 11801 standard. Both of these are very similar, and what they do is they specify, I'm going to work on an analogy here, they specify the shape of the road that we're going to be transmitting on. These are actually the specifications for an overpass for the United States highway system. So the standard is going to talk about how wide the lane should be. Maybe not how thick the concrete is, but what weight it needs to support. And I really like this idea of what's the lowest overpass that I'm going to come across on the highway? Because to complement the cabling standards, we have the application standards. And the one you're going to hear about the most is Ethernet. Ethernet actually comes from a standard from the IEEE, the 802.3 standard, and we can think of the applications as the vehicles that are going to run on our network. Now, if we followed the standards when we were installing our cabling, we punched down 4 pairs, we only went 100 meters, when the next device comes out, when the better access point, when the better camera, when the better card reader, when the better access control method comes out, we can just switch it out on the end and use the existing cabling, saving us a lot of time and effort in our upgrades. All right, so that said, what are some of the basics of structured cabling? In structured cabling, we're going to talk about up to 100 meters of cable, and the standard suggests putting 2 outlets at the endpoint, one of which needs to be an RJ45 connector. So we're going to have our 4 pair. Generally in the United States, we use unshielded twisted pair. This is UTP cable. Whether you use shielded or unshielded, category 5 or category 6, I don't care. It doesn't affect me. What I want to help you with is how you would test this installed cabling. Now, on one end, typically we're going to have a patch panel that serves as an administration point. And on the far end, when we're working in an office environment, we're likely to have some type of wall plate. Now, in an outdoor, or if we're installing a wireless access point in the ceiling, or we're installing a security camera at the entrance to a building, that may be a surface mount box and not necessarily a flush wall plate. Within the standard, we're going to talk about 2 different types of link models. The first one is called a channel. Now the channel includes, we can see this blue user patch cord on one end by the patch panel. Typically there's a 19-inch equipment rack here in the telecom room. And then on the far end of the cable, underneath our desk typically, or where the photocopier is located, the channel model also includes the user patch cord. And you would say, well, why don't we always test with the user patch cord? The user patch cord isn't always available. Sometimes we're going to add an extra outlet when we're installing wireless access points. Well, I'm only installing 1 wireless access point, but the standard recommends we bring 2 cables there. That gives us the flexibility in the future to add an additional access point. Again, the standard is the experience of the industry. What has worked well for me? What hasn't worked well for me? Oh, I didn't install all 4 pairs. That didn't work well for me in the past. Let me recommend that to people in the future. Now, because we don't always have the patch cords available, and the patch cords are designed to be switched out, what we first look at is something called the permanent link. And the permanent link measurement starts right at the patch panel, and it ends right at the communications outlet. So typically when we first do an installation, we'll test it against the permanent link limits. If it passes the test, great. If we buy factory-made patch cords, we don't need to retest. But if we're having a problem, the patch cords are there, we'll probably use the channel model for our troubleshooting. So after we have installed the cable, we put the cable tester, hey, here's a picture of a cable tester. We put that cable tester on the line, we're going to run a test, and it creates this. This is the product that we deliver to our customers. This is a guarantee, if you will, that the installed cabling should perform up to their expectations. Now, this is looking a little bit scary. We've got a lot of numbers and graphs and lines here. We have NVP and delay skew and next. Let's not be afraid of this test result, this test report, but first let's understand how to read it. if you've never seen a test report before, there are two very important fields to read from it. If nothing else that you remember from today. First, did the test result pass or fail? This seems obvious, but we want to make sure it passed. And the second field that's very important is, what did it pass? So if I had asked for category 6A material here, I did not receive a category 6A test report, only category 6. So take a look at what your test limit. Now, let's drill in and see if we can better understand what propagation delay, next return loss, and this cryptical insertion loss actually are. So this presentation is really going to talk about what each one of the parameters is, and then we're going to look at how we can find the distance to where a problem is on the cable. So this bumpy green line here is going to represent a single pair of cable. And these circles here, they're going to represent the electrons, the signal that we're going to transmit down the wire. Now, the first thing we need to know is the length of the cable. There's a length requirement. And this could be measured in time or in distance. When we measure it in time, that is something called the propagation delay, where I'm going to send these electrons. See, the clock is straight up 12 o'clock, and it takes them a little bit of time to get to the far end of the cable. They have 555 nanoseconds to get there. Now, if we want to figure out what the length of the cable is, we can take the amount of time it took to get to the far end, and then we're going to multiply it by the speed of the signal. This cryptical NVP, the nominal velocity of propagation, overrated. All it's telling us is the speed of the signal. We don't know the speed of the signal, and that varies slightly between the cables. So we'll multiply the speed times the time. That gives us the length, the distance to the end of the cable. Now, sometimes the NVP will be incorrect, and people go, oh my gosh, it failed. You must have done the NVP wrong. What is the NVP? Calm down for a moment, calm down for a minute, because again, one measurement is the length. And here we're looking at the details of a link. I did say that we get to go 100 meters, but in a permanent link test, we only get to go 90 meters. It gives us 10 meters, about 30 feet to add those patch cords on the end. Now, cryptically, this is saying that it measured 97 meters against a limit of 90, but it passed. That's because the NVP can be incorrect. So the standard gives us 10% of extra shape. I like to show this test result, however, because this test failed propagation delay. And there we see it failing, oh, even closer, failing propagation delay. The limit is 498 nanoseconds to get to the far end, and this took 499 nanoseconds. Yes, this link is 1 nanosecond too long. Remember, we want to be able to support future applications. So in this case, well, we need to move the wall about 1 nanosecond closer to the closet. Yes, I'm kidding, of course. We move the wiring closet 1 nanosecond closer to the end. That would be much easier. Okay, sorry, I digress. So really what we're looking at is, what is the signal strength that we're transmitting? And then what is the noise? We need to have enough signal to understand what's being said by the far side, and we need to make sure that there's not too much noise getting in the way of that. Now, the signal strength that we measure, we actually measure the loss of signal, and that's something called insertion loss or attenuation. So here's our friend, that single pair of Ethernet cable, and we're going to send this number of electrons down the wire, and when they get to the far end, fewer of the electrons are going to show up. We lose some along the way. Let's take a look at this a different way. Let's take a look at this with the screen from the tester. Now, the screen on the tester on the vertical scale is showing us the amount of signal loss in decibels. Decibels is a simple way of comparing two values. So decibels, we're comparing the signal that we sent with the signal that we receive on the far end. So the vertical scale is decibels, and the horizontal scale is frequency, megahertz, the frequency at which we're transmitting. Now we can see this red line here, and this red line is the limit line for the standard. That kind of the minimum height of the overpass, what the shortest overpass should be, and we see that it's going to 250 megahertz. That makes this a category 6 cable. Category 5E goes to 100 megahertz, and category 6A goes to 500 megahertz. So what causes the signal loss? Length. Think about it. If I'm standing next to you and I'm talking to you, you can hear me. But if you're on the other side of a football field from me, it's going to be harder to understand what I'm saying. So down below, we have the measured value, this multicolored line. This is actually the 4 pairs. They're kind of on top of each other. And here is a longer cable. This is a cable that's closer to the 100-meter limit, and you see that the measured value is getting up there close to the height of the overpass, close to our limit. It increases with frequency. You can see we're going up and to the right. As we get into higher frequencies, we have more insertion loss. Now, another thing to be aware of is that insertion loss also increases with temperature. So if you are installing your cable in a location that may experience elevated temperatures, perhaps you're installing it just underneath the roof of a warehouse in Phoenix, and you know during the day that cable is going to heat up, you're actually going to have to reduce the length of your cable because you're going to get additional insertion loss in the middle of the day as the temperature goes up. The standard actually has a chart to show us how much we need to reduce the distance based on the temperature that we're working with. All right, so there's our signal strength, and the other side to signal strength are noise parameters. And the first noise that we're going to look at is something called return loss. So again, with our single twisted pair of cable, and there are our friends the electrons. Now we're going to send the electrons down the wire, but as they go down the wire, they run into these dips and bumps, kind of like a speed bump, but technically it is an impedance variation in the cable. If we change the distance between the 2 copper conductors in the cable, that's going to change the impedance, and that's going to cause a signal to reflect back to us. So return loss is a measure of signal that reflects back to us. Now, I'm going to put 2 cables right next to each other, 2 pairs, if you will, right next to each other under the same jacket, and I'm going to transmit our friend the electron along one of these pairs. Now, as they're running in parallel, we have a problem where some of that signal will jump off, if you will. It's induced from one pair onto the adjacent pair. And when it gets to the adjacent pair, it's going to go in both directions. Now, if I transmit on one of the pairs and I listen just on the adjacent pair on the near side, that'll be near end crosstalk. Now, crosstalk, we remember back in the olden days when we had a telephone in our house, sometimes we would pick up that telephone and we could hear our neighbor's conversation. Some words would come through. That's exactly what this crosstalk is. It's that signal bleeding over from the adjacent cable. Now, on the near end, we measure it as near end crosstalk. And if we measure those electrons on the far end, that would be, you've got it, fixed or far end crosstalk. Let's take a look at what this looks like on the cable tester. So again, here are 2 pairs. We transmit a signal on one pair and we listen on the adjacent side for a coupled signal that's come across. Now, on the tester, what this looks like, the vertical scale, the signal in decibels, which is comparing what we sent out to what we got back, and then on the horizontal scale, the frequency. Again, that red limit line, the minimum height of the overpass, and up above we have 6 different pair combinations making these jagged lines up here. The important thing we can see is that they are all above the limit line, so we don't have an overpass on our highway that's too short. What is it that causes near-end crosstalk? Well, actually, a lot of it comes from that great RJ45 plug. Don't get me wrong, I really like the RJ45 plug. If you've ever had the opportunity to travel outside the US, every country has a different power outlet. Okay, not Canada, but other countries have a different power outlet. So I need to bring a whole bunch of adapters with me so I can plug in my laptop, so I can plug in my hairdryer, so I can plug in my cell phone to charge it. But wherever I go, the data outlets are always the same. It's always an RJ45, every laptop. every wireless access point, every device that can connect to the network. My television now has an RJ45 jack on it. Unfortunately, the plug that goes on the end of the patch cord, they put the 4-5 pair inside of the 3-6 pair. They did it to follow the old telephone company rules, but that does make for some extra near-end crosstalk. Badly made or damaged cable can cause crosstalk. If we untwist the pairs of the cable too much, that can be a source of crosstalk. Again, this is noise, the interference from one pair to the other one. Now, another problem happens is testing against the wrong limit. You might say, well, I'm going to be running 10 gigabits Ethernet here, so I need you to test this cable to category 6A to make sure it will pass 10 gigabits Ethernet. Well, if you didn't install category 6A cable, that's not going to pass. And there's another reason for us to do the test. Boxes of cable are not generic. They do not say in giant letters what they are. They say in giant letters who made them. But you got to get into the fine print to see, is it 4-pair cable? Is it category 5? Or is it category 6? And somebody might just accidentally install the wrong cable. If we certify it, we'll catch that. Now, another parameter, and this is a little bit more complex, but I think very important for the situation that we come across today, is the testing to support power over Ethernet. A lot of times people will say, how do I support power over Ethernet? Well, we've looked at the Ethernet side, the length, the signal strength, the noise. For the power element of this, what we want to look at is the loop resistance. And field testing today of category 5, 6, and 6A cables does not require us to test loop resistance and something called resistance unbalance. We want to make sure that the resistance of each leg of the cable is similar. If we don't have a similar resistance value in each leg of the pair, it's going to screw up our ability to support power over Ethernet. So these loop resistance tests are a way to assure that the installed cabling is ready to support power over Ethernet. Now, they're specified in the 568 standard, and they're specified in the application standard from the 802.3, but they're optional for field testing. The 1152 standard, don't worry, this won't be on the test, but if you remember it, I'll be impressed. The 1152 standard specifies the performance of the cable tester, what tests we're going to run, and how accurate they are. So if you know that you're going to be installing devices that are going to run over power over Ethernet, I suggest selecting test limits that include this well-identified plus PoE. Let's take a look at how that works. Now, if any of you have ever worked with one of our cable testers before, you'll be familiar with this situation. Here we are selecting the test limit. We can select 6A. Here's that permanent link that doesn't include the patch cords. The channel test that does include the patch cords. If you don't have the patch cords yet, you've got to test to the permanent link. If you're troubleshooting, we'll use the channel limits. And then we have our plus PoE limit. So let's select just a basic category 6A permanent link limit. This is the default test that's in the tester. And you get home and it's so excited, my new Fluke tester, and you push test on a link you know that's good to make sure it works. And it says pass, but it gives us this cryptical letter I for the resistance value. Oh no, it's not passing. What's wrong with resistance? No, it's okay. We always measure resistance. Our electrical engineers in the factory are kind of hung up on this, but we're just calling it informative because there's no limit. It's not required by the standards. So I can't say whether these values pass or fail. Now, if I select the plus PoE limit, we are going to use the values described in the standards for resistance. And now that we have a limit, we're able to say whether the values pass or fail. We've got a height requirement for the overpass there. All right, so now we've got our Ethernet with our signal and our noise, and we've got our power with our resistance, but we're going to put together those signal to noise ratios because, again, as I was saying, I need more signal than noise for this to work properly. So the first one we're going to look at is the attenuation to crosstalk ratio. Actually, it's the only one you're going to look at today. So please don't be worried about us taking too much time here. All right. So the attenuation to crosstalk ratio really applies when we're working with two-pair applications like 10 base and 100 base T. And let's go back to our signal, our electrons. So what we're going to have here is our workstation with the network interface card, and here's our LAN equipment, our computer, our laptop, our wireless access point, our security camera, and it also has a transmit and a receive. So here we go. We're going to transmit. The blue signal is going to be going from left to right, and the pink signal from right to left. Now, as those signals travel down the wire, there's going to be some interference. There's going to be that near-end crosstalk that's going to be induced to jump across, and the signal that we transmit is going to attenuate. So we see that the pink signal, as it went from right to left, from the transmit to the receive port, from the TX to the RX, we have less signal arriving. But what's important is the signal is greater than the interference that we have. As long as we have more signal than interference, remember my example of talking to you all the way across the football field. Today on a football field, I can do that. There's no one there. Now, if there's a football game going on and I'm trying to talk to you on the other side of the stadium, especially here in our particularly noisy stadium in Seattle, no, too much noise, you're not going to be able to hear what I'm saying. All right, so I wanted to use this graph that shows the signal to noise ratio together to explain quickly the performance differences between category 5E, category 6, and category 6A cable. So the first one we're going to look at is category 5E. Here is our limit line, that height for the overpass, and it goes out to 100 megahertz. So our available bandwidth is the space below this line and above the 0 dB while I still have signal. So this is going to be the available bandwidth for us where we can do our transmission. Now, I hear a lot of back and forth on what cable category 5E is designed to support. Category 5E will certainly support 10 and 100 megabits Ethernet. Will it support gigabit Ethernet? Absolutely, all day long. I'm not the person who sells cable here. I'm the person who tells you how to test the cable. Now, they came out more recently with even some higher speeds than gigabit Ethernet. They call these N-base T, and that can be either 2.5 or 5 gigabits Ethernet. Now, when they developed 2.5 and 5 gigabits Ethernet, they really wanted them to work on category 5E cable. There's more category 5E cable installed than anything else. So those will run on category 5E cable. You can get up to 5 gigabit Ethernet. That is a lot of bandwidth. Now, some people will install category 6, and we see the difference between category 6. Let me go back for 1 second and notice that the top of our limit line here is about 58 dB. We'll see that when we jump to category 6, it's going up to about 62 dB. So it's higher up, and it goes out to a higher frequency, to 250 megahertz. Some people will install category 6 instead of 5E because it costs about the same. The installation cost, the space, the termination, that costs the same. The hooks, the tray that you're going to be putting in the cable in, that all costs the same. And that little bit of extra bandwidth is going to give us some extra space, some extra headroom to make sure cable doesn't deteriorate over time. Now, the other one that we hear a lot about today is category 6A. Category 6A is going to go all the way out to 500 megahertz. So it has dramatically more bandwidth than category 6 or category 5E. And it is designed to support 10 gigabits Ethernet all the way out to 100 meters. 10 gigabit Ethernet is enough bandwidth for you to transmit full line rate uncompressed streaming video. Now, when we're talking about which one we should install, the standard does allow all of them. But the current thinking today, when we're installing a wireless access point, we know that the wireless access point in the air, in the wireless, when we talk about Wi-Fi 5 or Wi-Fi 6, that's 802.11 N, 802.11ax, I think is the next set of letters that's coming. I prefer that they call it Wi-Fi 6. That is going to exceed 1 gigabit in the air from your cell phone up to the wireless access point. So if you have multiple radios in a wireless access point, you could be exceeding 1 gigabit per second. And that's today. In the future, we're going to have greater speed. And that's why you're going to find the recommendation that for wireless access points, we install category 6A cable so that we have the additional bandwidth available to support those new wireless access points in the future. All right. Oh, and did I forget to mention category 8? There is a category 8. Category 8 goes all the way out to 2 gigahertz. But as you recall from our impedance, our insertion loss study, as we increase the frequency, we have less signal strength. So while category 8 can go all the way out to 2 gigahertz, a much higher frequency, because we're operating at that higher frequency, we're reduced to only 30 meters, about 100 feet of distance that we can work on. So category 8 is sort of a specialized application that we see in data centers, but I don't see a lot of that getting installed. Certainly 5E6 and 6A are very prevalent, available, if you will, in the market. Okay, so we've installed our cabling properly and something doesn't work. Can we do the troubleshooting? Let's take a look at how we're going to look in the time domain to find the distance to problems. Okay, so here we have a potential return loss problem, a signal being reflected back to us. So we're going to look at how we can identify the distance to a return loss failure at 2 separate locations. This is a little bit technical, but please appreciate if we're putting in fancy category 5E or fancy category 6 cable and it doesn't work, I'd like to figure out where the problem is. That's what we're going to look at here. So there are friends, the electrons. We're going to send them down the wire, and if our problem is close, the signal is going to be reflected back to us sooner than if we have a problem that is further down the wire. That problem that is further down the wire is going to take a longer time to get back to us. So yes, we can tell the difference between problems that happen close to us and problems that are happening far away. Now, the same thing with near-end crosstalk. Here we've got our 2 pairs together. We're going to transmit a signal. We're going to have some crosstalk on the close to us. We're going to have some crosstalk in the local patch panel. Now that signal comes back sooner than if we have crosstalk that is at the connector at the far end, perhaps underneath the desk of our user. So we can see the difference. A near problem is going to come back sooner, and a problem that is farther away is going to take more time to come back. Now, why is this important? Let's take a look at that test result again. And just for fun, instead of having the limit line being red, I've made the limit line blue here and the test result and the measured value red. So again, when we're looking at a test result, and here's a near-end crosstalk problem, we have the strength on the vertical scale in decibels versus the frequency where it's operating. The standard requires us to report the measured interference in the frequency domain. So this link that was built, first of all, we see this failed. See that measured value is below the limit line. So on that electronic road that I built, there's an overpass that isn't tall enough to support the trucks that I want to send. Well, let's take a look at what this link is. I can see that the failure is happening at a lower frequency. If this were 100 megahertz, it looks like it's happening at about 20 megahertz, but I don't know where it is. Now my link has a patch cord, a 30-meter cable, an administration point with 2 meters of category 5, and then, somebody installed 30 meters of category 3 cable. Hey, the salesman told me that it was really cheap and it was so good I didn't need to test it. He actually suggested I not test it. Boy, did that save me time. Well, It didn't, because we're failing and we don't know where. Now, within the cable tester, we have a functionality called, you may have heard of TDR, time domain reflectometry, that we use to find the distance to impedance variations. You may have done that on telephone cables if we wanted to find the distance to where a telephone connection perhaps had some corrosion with it. Well, we have TDX, which is time domain crosstalk analysis. So this is showing us the distance to where the crosstalk is happening, and we can see at this first connector we've got a little bump. At the second connector we have a little bump. Now that category 5 cable has very few events in it. We've got a bump here for both ends of our 2-meter patch cord, and then farther along, oh my gosh, look at all these crosstalk events. I can use this and it can help me to figure out the distance to where I need to go to find a problem. And this is what it actually looks like on our new DSX 8000 cable tester. The marketing department got their hands in this, so instead of just being time domain crosstalk analysis, now it's high definition time domain crosstalk analysis. That makes it much better. So again, here's our first connector. Here's the second connector before that short patch cord, and then here's that category 3 cable, and we can see all those bumpy lines in there. Now, don't be afraid. You don't have to hire an expert technician who's able to interpret this graph. The tester actually has a feature called fault info, and fault info is just going to tell you, hey, the cable's damaged. That's your problem. So pretty straightforward. We noticed that we failed, and in fault info it's saying, hey, we have a cable problem. So even a regular common technician, a technician that we could afford, is going to be able to find the distance to where the problems are. All right, so summarizing our fault finding, first thing we have to make sure we have is connectivity. Do we go to the far end of this cable? We want to check the length. If the cable's too long, not enough signal is going to be getting out. And what that might mean in the Ethernet world is, rather than connecting at 1 gigabit, our link is going to downshift and connect at a lower speed, 10 or 100 megabits. We want to make sure we have near-end crosstalk, and this is after we have connectivity and we know that the length is good. After near-end crosstalk, we'll check return loss, that signal that's reflected back. Now in 10 and 100 megabits, return loss is less important because I transmit on one pair and receive on another pair. But when I go up to gigabit Ethernet, I'm going to transmit and receive on the same pair at the same time, bidirectional communication. So that reflected signal that comes back to me, that's noise, that's interference. Far end crosstalk, attenuation. Now we've put DC loop resistance at the end of the list here because this presentation originally came from long before Power over Ethernet existed. If you're having trouble with your Power over Ethernet, you might want to take a look at the DC loop resistance. One of the places that I really see this coming out is when people use, I'm going to call it fake category 5 cable, because according to the standards, according to the 568 standards, category 5E cable must be made of pure copper. You cannot mix other metals in there. And I've seen cases where, in order to make a cable less expensive, people will look for a different conducting metal. It might be aluminum or it might be steel. The issue with aluminum in the core of your cable, you can put a copper around it. There's a cable called copper-coated aluminum, but copper-coated aluminum cannot be category 5E because while aluminum is conductive, it is not as conductive as copper, so you're going to get too high of a resistance. So if you save money by buying fake category 5E cable, many times it'll even say CCA. That's not going to support your Power over Ethernet application, so that loop resistance test is very important. All right, let's come back to that test report again and see if we're not feeling a little bit more comfortable in reading this test result. So first, we're checking to make sure that it passed, and it did. That's very important. And we can see the test limit here. The test limit is 6A plus Power over Ethernet. So we're measuring the loop resistance and the resistance unbalance. We know that the nominal velocity of propagation is the speed of the signal in the cable, which we use to measure the length. We know that the propagation delay is the amount of time it takes to go from one end of the cable to the other one. Here's our insertion loss graph, which we know is the strength of the signal in the cable. We know the near end crosstalk is the interference. Now we measure the near end crosstalk from the main tester to the smart remote, and from the smart remote back to the main tester. We're going to report both the worst margin, that's where we're closest to the limit line, and the worst value, where we measured the worst value. Now down on the bottom of this test report, we're going to see those ACR values, the attenuation to crosstalk ratio, both on the near end and the far end. And finally, our friend return loss. And even down here on the bottom, it's telling us what applications should run on this network. 10 megabits, 100, gigabit Ethernet, 2.5, 5 gigabit, even 10 gigabit Ethernet is going to be supported on this category 5E cable. All right, folks, there's the technical part, a little bit of commercial stuff. Our most common solution, the bread and butter, our day-to-day business, is the Versiv platform. All four of these testers have the same device on the front end, the same screen, the same look and feel, the same linkware software to administer the test results, but we have a copper version, which is the DSX 5000 or the DSX 8000. We have a fiber tester that is a light source and power meter that will tell us how much light is coming out of our fiber optic cable. We have an optical time domain reflectometer and OTDR to tell us the distance to where fiber problems could be. And we even have this special video camera so we can inspect fiber optic cable to make sure that it's clean. Each one of these is a different module on the back of the Versiv platform. And in the market of cable certification, this is probably the most common cable tester you're going to find. We have simpler testers because sometimes your customer isn't going to pay for certification. I'd like them to pay for certification. I can charge them more. I can install better components, but hey, it's the contract that matters. And also just for the day-to-day troubleshooting, does this cable have continuity? Is there a switch attached to the far end? The Cable IQ and the microscanner are very practical products. One last comment on the Cable IQ. The Cable IQ is the least expensive solution we have, about $1,000, that can store test results. Sometimes people had a customer, they were installing bank branches. They were driving all over West Texas days. They had a crew that was out installing about 10 drops in a bunch of rural bank branches. The customer didn't want certification. Got to deliver what the customer wants. So they were using a Cable IQ because they could save those 10 to 15 drops in each branch they went to. Simple tools for fiber power meters, fiber cleaning kits. We want to make sure the fiber is clean before we plug it in. Fiber will be a different presentation. And then we also have some of the handheld tools. If there is anyone still working on the outside plant telephone system, yes, we make butt sets and the punch down tool snips, cable strippers that can be used. Now, I want to go back to the microscanner for a minute because this has been one of our most popular solutions these days. Basic microscanner runs about $500, and this kit, a little bit more than $500. At the end, I'm going to show you the contact information for ADI so you can check the exact price. But if I have to work day in and day out with RJ45 cables to support Ethernet in different customers' network, in my own network that isn't well identified, the microscanner PoE is a great solution. It's going to tell us continuity. How long is the cable? What's on the far end? It will tell me if there's a switch on the far end. It will tell me if the device on the far end is transmitting PoE and how much PoE is being transmitted. Today there are 8 defined classes of power over Ethernet service and a handful of proprietary ones like UPoE. Now, if I plug into an outlet and I don't see a switch on the far end, and I see that it's open 30 meters, 100 feet away, I need to find what is the port on the patch panel that I'm attached to. And if it's not identified, this this probe here, an inductive probe that we can use, is extremely useful. I'll send a tone down the cable and I can find the port of the patch panel that it's attached to. This toning probe, I should have picked a picture that shows the bottom of it. The base of it here has another RJ45 outlet, so I can plug in. It has 8 LEDs and it will beep through them to tell me if I've got continuity on all the conductors. Now, sometimes I go out to a customer's network and they have no identification and I need to identify a bunch of outlets. I can use these remote identifications to plug into 6 ports. Yeah, I know one is missing. One's this this one on the top of the tester here. So I can identify 6 ports on the patch panel without having to walk back and forth a whole bunch. All right, folks, that is my pitch, and I'm going to switch over and take a look and see if we don't have some questions out here that we can answer. Bear with me just a moment.
Hey, Jim, while we're waiting for questions to queue up, why don't we let Mike speak? And for those on the line, please put some questions into the Q&A box, and we'll be back right after Mike Aceta speaks. Mike?
Thank you, Mike. Everybody, can you hear me?
Yes, we can.
Good. Okay, great. Thanks. Good afternoon, everybody. Thank you for taking your time to join us today for the webinar. My name is Mike Aceta. I'm the general manager for the Enterprise Connectivity Group here at ADI. So we're pretty much the Datacom group. So we have salespeople all over North America to help service you kind of from the rack to the jack, as we like to say, and with tools and testing also being encompassed in that group. So Fluke coming on board, I guess a little less than a year ago, has been a great addition to our line card. They are the top brand when it comes to testing equipment. My team will follow up this call with a call out to you guys just to introduce themselves and ask you if there's anything further. So Jim went through a lot of great information, but if there's more in-depth training you need or conversation you need to have about the equipment or what it can do, my team can then facilitate that with the Fluke representatives. Once again, we're here, as Jim said, they're not selling cable, what we do. So if you have any questions about cable or connectivity, racks, power, cooling, all those kind of things that we use here in the Datacom world, please reach out to my team. If you're talking to your local branches and they have some questions, you can just ask them to direct you to my team, and we can get in touch and find the best solutions for you. But once again, this has been a great training in my opinion. Fluke is an awesome partner. We're really glad to have them as part of the ADI family, and looks like some questions are popping up, and I will throw it back to Jim and Mike Maston.